Hello, I'm going to look at what's inside a heat pump. It can look really complicated in there. So I've got this little model, which is simplified. I made it out of bits and pieces, really, to show the basic components. So let's have a little look at this. Then I'll do a diagram. Then look at the parts individually, including inside one of these compressors, and maybe afterwards talk a little bit about how it actually works. So let's get started. Let's have a little look right round it. So there's a heat exchanger at the back, an air heat exchanger where the air comes through, and at the front of the unit here there's a fan, so you can see that the air can pass through the unit out of the fan, and it emerges colder than when it went in. And on the side here, I've got the cover removed, and we've got another heat exchanger here. This one transfers the energy to hot water, and that flows to the house's radiators, underfloor heating, or the hot water cylinder. We got this compressor. Now this is an electrically powered bicycle pump, really. A bicycle pump is a compressor. So we have this, and it's connected to the heat exchangers with a refrigeration circuit with a refrigerant. So the refrigerant isn't really just circulated. The important thing is there's a pressure difference between the cold, low pressure side and the hot, high pressure side. So here's a diagram that some people might like, and it just shows the components of that heat pump, an air source heat pump. And this is the finned air heat exchanger, and this is the fan, and air is drawn through from outside and out of the front. There's also the condenser, the hot side of the system. This is piped to the radiators or the hot water cylinder. And I've just put an illustration here of something more representative of what we're using, the stainless plate heat exchanger. But this is basically some sort of coil in a shell. Now the compressor is in the middle, and that's drawing vapor from here, compressing it to a high pressure here. Now the condensed liquid comes down here to some sort of valve. In the model and in a fridge, it's just a capillary pipe. But in any heat pump, it will generally be an electronic valve, particularly if the compressor is a variable inverter type. So let's look at these components individually. I'll start with this air heat exchanger here. I think you can probably just about see through it. So it's a copper pipe, a network of copper pipes, and to increase the area, there's these very fine lots of fins. There's about at least a square meter's worth of aluminium fin there, very fine, very fragile. And you can see on the pipes here, they're quite small bore. On this particular model, it's just one loop, but most heat pumps, there'll be multiple ways of small bore pipe. And the heat exchanger usually curves around the ends to make more use of the space, really. I'll say on this model, which is air to water, a normal air source heat pump, we've just got one air heat exchanger. Of course, if this was air to air, we'd have another one of these, probably in a unit inside the house. But this is air to water, so we got this water heat exchanger here. So here we have such a heat exchanger. This is actually water to water. It's not a refrigerant one. It does show the plates rather well. Now, if you see that, it's like a stack of plates. I think there's 18 plates on this one. These are brazed together in an oven with no oxygen. So if you can see, they're sort of corrugated ribbed, and they're stacked up. And how they work is that they've got separate passageways alternately. I've got one sawn in half there, and you can see there's lots of passageways that caused by these multiple plates in there, and they alternate between water, refrigerant, water, refrigerant, water, refrigerant. So heat is exchanged, but the fluids stay separate. Now, this one actually is a refrigeration one, and you can see there the end plates are very thick because this has to take a higher pressure than this one. So in an air source heat pump, you will have one of these to transfer heat away to the water from the refrigerant. This is the condenser. Now on a ground source heat pump, you'll have two of these. You'll have one for the source instead of the air heat exchanger, and you'll have one to output to the heating in the house. So that's the two heat exchangers. The other main, or the main component, is the compressor. So we'll start with actually a fridge compressor. This is just a fridge compressor to start with because it's very simple. And this will, your fridge will have one. So this is in a welded sealed case and usually held on springs so it doesn't vibrate too much. And if you look, there's the motor windings here, and there's a rotor in the middle that spins. And if we look on the top, you're going to see a very simple crank as it turns, and that causes the piston to go up and down in that bore. And then we have this little valve plate which has some little reed valves on, which goes there on the cylinder head. So that then will compress the refrigerant in here. It sucks from the shell, and then the output is this little capillary pipe which goes through the shell out to the hot side, the back of the fridge in this case. So that's the sort of compressor used. It could be used in a heat pump, but they are generally a bit more efficient. So this is a type of compressor that's more typical of an air source heat pump. It's a rotary one. And I've cut the top off and the bottom off. And in the top, you can see the electric motor there, a bit like the other one. And on the bottom, to show you that this is the suction pipe into the compressor. And that's the bottom. If I just take this bearing off, there, you can actually see the workings, and it's a little offset roller. I rotate that round. You see the roller going round. So the suction pipe goes in here, put a little arrow there, and then the discharge comes here through into the shell. And as you can see, there's a vein in the middle there. As it rotates, this chamber, the bottom, gets larger. It gets to this point here where now that chamber there is shut off. And at the top, it gets smaller and smaller. The refrigerant is squeezed down the pipe into the shell. That just keeps going round and round. Sometimes there's two rollers, twin roller. Sometimes there's one. And this one, the high pressure goes into the shell, which is maybe surprising in the sense that the winding has to dissipate its heat somewhere. This can be completely insulated, so that heat is transferred to the refrigerant. It seems surprising to use the hot side of the system to cool the motor, but it works. It's got some advantages. And this sort of compressor is energy efficient and very rugged. And of course, this is an inverter type, so the motor speed can vary as required. So now let's look at another one, which is a scroll compressor. This is off a bigger unit. The last one was probably 3 or 4 kilowatts. This one is more like 16. It's quite a big one. So this would be at the top of the compressor, motor at the bottom. This is just the top bit. And here we go. And there's a thing like that. Now these are only possible, it's only possible to make these types of compressor with a mass production, very high precision techniques. What they do is these two parts go together. They don't actually spin, but they sort of orbit like that, or gyrate, I don't know the actual word. And similar to the last one, really, it's drawing in the vapor and sort of squashing it as it goes. This is likely to be the most energy efficient compressor, but it does cost more to make. Generally, bigger compressors are this type. Not necessarily better than the roller, but often chosen for various reasons. Now, interestingly, there's no seal in this. It's just very high precision. And the surfaces are in contact. There's oil in there. And it's interesting because they don't really wear out. I took out the oil before I cut it to bits. So look at that. That is as clean as it went in. Now, on a car, of course, the oil needs changing. It gets dirty, and there'll be some metal within the oil. But with this, the wear is almost zero. I mean, this has done quite a few hours of work, and you can see the surface is a bit shiny. And these can keep going and going. It's very rare to actually see any amount of wear, and in fact, these don't tend to wear out. Now, the first compressor I showed with the reed valves, they do actually suffer from, they say the performance deteriorates, but with the scroll and the roller, they seem to keep going nicely. Okay. So one thing I haven't spoken about is the refrigerant in the system. And the nearest I have to a refrigerant is what's in this lighter, which you can see it's liquid, it's under pressure. There's no air in there, it's just either the liquid or the vapor. And in a heat pump, we need a fluid that can evaporate on the low side and condense in the high side. And that will generally be an oil-based compound. And there's various different types, so I won't go into that now. Package unit heat pumps, meaning the heat pump with all the bits in one place, they're all welded up, sealed up, so there should be no leak. So the refrigerant should stay in the system for its lifetime, in the same way as a fridge. You very rarely hear of a fridge losing its refrigerant. So we've looked at the compressor, some heat exchangers. Now, one thing I haven't said, and I haven't done, is now back to this diagram. With the finned heat exchanger on an air source heat pump, water will collect because there's moisture in the air, and as we cool it down, it'll probably be below the dew point and water will condense, and that will run away. But as the outside air temperature gets below around 5 degrees centigrade or below 40 Fahrenheit, then the water will start to freeze. And as it starts to freeze, you get a little film of ice, and that actually reduces the airflow, and quite quickly it starts to freeze up. So there's a mechanism to reverse the system to melt the ice. Effectively, what happens is these two pipes are swapped over. So now we're taking heat from the condenser and sending it back out here for something like 4 minutes to melt the ice. So it's not much of the total, but I'll show you the valve that is used to perform that reversal. So let's look at a reversing valve. I've got one here. And what it does is reverses the inlet and outlet to a compressor, really, to reverse the whole system. It's got 4 ports on it. And in there is a sliding valve. Now, this is actually very similar to a trumpet valve. And I'll just show you on a diagram how it changes. Interestingly, before I do that, of course, to move that valve across would take quite a big solenoid valve. You can see a little valve here. And rather cleverly, there's little tiny capillary pipes. And what this actually does is uses the pressure across the system to actually drive the piston. So this solenoid valve just opens a small valve here, we call it pilot control valve. So nothing will happen if the compressor is stationary and this changes, the valve won't actually move. It's only when there's pressure in there that it'll push itself either way. But of course, if the compressor's not running, it doesn't need to move anyway. So let me just show you what it does by sharing screen. So you can see here on the left, this is in one mode where the discharge from the compressor goes down this pipe, and the suction here comes from this pipe. And then as the valve changes, the routes swap over, and now this one is going across to the right, and this one's sucking from the other way. So it's a four-way reversing valve, and that's universal on every air source heat pump. So what else will you have? Now let's talk about the refrigerant control valve. So on our little model and on your fridge is something as simple as that. Now that looks like a copper wire, but it's not. It's a capillary pipe with a very small bore, less than 1 millimeter, I think. And what it does, it's the restriction between the high pressure condensed liquid and the low pressure side. There's got to be a pressure difference between the high side and the low side. You need some sort of valve to control, to sort of meter through the quantity of refrigerant in the high and the low side. Now, this is a little bit cleverer than it first seems. It's not just like an orifice, because as it comes in as a hot liquid, high pressure liquid, at some point down this pipe, it will start to vaporize as it becomes a low pressure liquid. And as it vaporizes, the pressure drop increases, and it's actually self-regulating to a point. Good enough for a fridge, but not good enough for a heat pump. Good enough for a little model, though. But let's see what heat pumps generally have. And they have something like this, which is an electronic expansion valve. If you can see it, you can see it if I hold it up there. And what it has is a little needle and a seat and a motor on top. And this is controlled electronically, opened and closed. It will close off when the system stops and then modulate to keep the refrigerant flow rate correct so that the evaporator surface is fully utilized. But that's automatic and nothing you can do to change that. So what else might we find in an air source heat pump? Well, there's probably one or two of these. This is a pressure switch. So there'll be one on the high side. So if, for example, the water circulation pump stops for any reason, then the pressure will go up. This one is just a cutout switch, and it will stop the compressor, shut the system down. There may be one, ideally, on the low pressure side as well. So if the pressure got too low, if the fan stopped working or some other reason the refrigerant was lost or the valve malfunctioned, then this could stop the system going too low in pressure. And there may also be a thing that looks just like that, which is a transducer, which sends out a signal. It basically records the pressure, and that's used in the control in some way. And you may see something like this. I mentioned earlier that the refrigerant has to be very dry, and inside a device like this, it's a dryer, and it's got a little bit of a equivalent to silica gel. In the old days, it was silica gel, in fact, but now they use something else. And it just takes any small little bits of moisture in the system. It's also a filter, but in the factory, the heat pump should be put together so cleanly that there's actually no bits to filter out anyway. So that's the dryer. Now, another thing you may see in a heat pump is something a bit like this, which is actually pretty well an empty vessel. Now, a heat pump has to work over quite a wide range of temperatures, from very low source temperatures to high source temperatures, and also the outlet can either be heating, underfloor heating at quite a low temperature, or hot water cylinder at a very high temperature. Now, in the system, there's liquid and there's vapor in different parts, and the quantity or weight of refrigerant in the vapor form or the liquid will vary due to the pressure and the temperature. So the actual quantity of charge, the quantity of refrigerant in there, will need to vary depending on the temperature conditions. So a vessel like this can act as a bit of a reservoir. Often, if you look at old refrigeration equipment, it has a very big reservoir, plenty of refrigerant. But of course, they want to design the system down for the minimum amount of charge, which is better environmentally. So it's a bit of a compromise, but some form of reservoir is needed. If nothing else, it can be needed for the defrosts. Okay, so I did say I'd say how a heat pump works. I'm just going to use this model to briefly discuss that. This is the compressor here, and I don't know if we can see this, but the outlet here, the high pressure gas goes round to the top of the condenser. So that's a high pressure gas. And then the other connection on the compressor around here goes to the top of the evaporator. And then, I don't know if you can see that, but in there is that little capillary pipe, which is really joining the two. So what's happening is that our compressor here is drawing vapor off of this evaporator, off this heat exchanger. Now, if the fan isn't running, the refrigerant in the pipes will be changing from a liquid to a vapor. And when that happens, they'll get colder and colder. So if the fan doesn't run, this will get colder and colder and the pressure will go down. But the action of the fan bringing air through it, in fact, transfers heat into these very cold pipes and continues that evaporation process. So the vapor goes round to the compressor, is then compressed, comes out of the high pressure, hot vapor. Now, the actual energy gain is not really to do with that compressing to a high pressure. The energy gain is the liquid turning into a vapor. That's where the energy comes from outside. It's then compressed, it will go to a high temperature, but then it goes into the condenser. Now, if there's no water running through that condenser, this will get hotter and hotter, the pressure will go up. So actually, by the action of water coming through around the radiator circuit, it will take heat away. The refrigerant will condense on what is relatively cold to it and run back to a liquid, still at high pressure. And then that will go through, it's metered through that little coil and goes back into the evaporator, and the whole circuit starts again. So in a nutshell, that's sort of what's happening. And the actual energy consumed by the electric motor in the compressor is less than the total heat delivered here. In fact, the heat here is a sum of the heat extracted from here, from outside, and the electrical input there. So this thing we call the COP is the ratio of how much electricity goes in here compared to how much heat comes out there. So typically, a heat pump may have a COP of 3 or 4, and this little compressor, which is probably 300 watts or so, could, let's say, extract 600 watts from here. There'd be a total of 900 watts here. That's in a nutshell how a heat pump works. If you found that interesting, do hit the like button or follow the channel, and I hope you enjoyed it. Thank you. Goodbye.